Okay, hi, I'm Elizabeth, and I'm going to tell you today why I think dust is interesting. And specifically for direct imaging, dust is interesting because almost every directly imaged planet, in fact, every planet until 2 weeks ago that we directly imaged, was in a highly dusty system. And often that dust is really complex and interesting as well. So, for example, Beta Pic has this warp shape. HR 8799 actually has two separate debris rings with a gap in between, and the planets line up very nicely with where we think the gap is. And that makes sense, because planets is quite a good explanation for why the gap might have been cleared. So taking that on board, we've been doing a survey of 37 targets, each of which host multi-belt debris disks, and trying to find the planets. So there's 3 reasons we're doing that. Number 1, like I said, it makes sense. It might be a good way of spotting where these planets exist and trying to find them. Number 2, we can actually use the dust and the interaction between the dust and any planets that we find to find dynamical masses, which we can then compare to the luminosity models that are normally used to find masses and work out whether the theorists understand what they're doing. And number 3, this is a paper which came out actually on the archive yesterday, which my collaborator Andrew Shannon has written, where he thinks he can predict a lower limit for the mass that must be present in the debris system for it to have cleared within the lifetime of the system. And sometimes that limit is quite close to the limit that we get to with direct imaging, so that has some potentially interesting consequences as well. So I haven't got any results yet. One day I want to know whether planets are more common in multi-belt systems, but for a bit more of the nitty-gritty and some of the details of my data reduction, please take a look at my poster as well, number 32. Cool, thank you.
Hi, my name is Jason. I'm a grad student at UC Berkeley, and I work on a Gemini Planet Imager to directly image exoplanets. So what I'm talking about today is a new robust statistical framework to measure the astrometry of directly imaged exoplanets, and in particular, we apply this to the exoplanet Beta Pictoris b. So one of the issues with directly imaged exoplanets is PSF subtraction. So we had to remove the stellar PSF, and we do this with principal component analysis. At least I do it. But when you do this, you actually, your planet signal leaks into your principal components and actually distorts your PSF. So you can see these black lobes next to in our data. These are artifacts of the data reduction. We developed a way to actually forward model this leakage of planet signal into our principal components. And you can see these are 4 models in our data. You can see how they resemble each other and give us much more information on the location of the planet. So then we put this into a Bayesian framework using Gaussian processes to model the correlated speckle noise in our data set to estimate accurate error bars. Then we use MCMC to sample the posterior distributions, and we're able to get 1 milliarc-second astrometry on Beta Pictoris b. This is 2 to 3 times more precise than previous analysis on the same data set. Next slide. So we do this with 12 epochs of GPI data, and then we combine with previous astrometry and fit a Keplerian orbit using MCMC to sample the possible orbits. And we find that Beta Pic b will definitely not transit, so unfortunately there will not be an opportunity to look for the transit of the exoplanet next year. However, the Hill sphere of Beta Pictoris b will transit. So this is the radius of which there could be circumplanetary material, so we can look for things like rings, moons, circumplanetary disks. And this is going to happen next year, and you can come to my poster if you want to learn more about it. Thank you.
Hi, so my job description is basically to find planets for direct imaging using GPI. So if you know anything about the number of planets we have found, you know I'm doing a terrible job. But so basically, so here at the bottom right, you have an example of data we're playing with. So the host star is hidden behind the coronagraph, behind the mask, and a planet will appear as a bright blob somewhere in your image. So that's 51 area B that GPI has found. So whenever you want to find a known signal in some noisy data, what you do is what we call a match filter. So the idea of a match filter is to project a known model or template everywhere in your data. So the cute name for that is cross-correlation. And you're looking for the peak in correlation. That's where your planet hopefully is. So the problem with direct imaging is that our planet model, our planet PSF, is highly distorted by the data processing, the PSF subtraction that we have to use on our images. So here you can see the distortion. So we have to predict this distortion to be able to have a good model for match filter. But this is hard. Luckily, someone derived the math for that, and so I implemented it for GPI. So next slide, please. And so to show how better modeling the distortion do compared to existing algorithm, I injected fake planets, so one in each circle, in some GPy data. And you can see that a bunch of planets that were not found in the regular approach are well detected using the forward model. So the forward model is the PSF where we modeled the distortion. Thank you.
Hi, I'm Tsuguru from Japan, second year PhD student. And my recent work with high contrast imaging of giants with arbitrary trends. And some giants show the radiosity trend like this, and like this. However, radiosity trends indicate the outer companion or planets. However, there is a degeneracy between the distant planet. It is like it locates at about 10 AU, or the outer further stellar companion locates at 100 AU. So the next slide, please. And so we did direct imaging observation to confirm which object makes the radiosity trends, and the result is shown here. And we detect the 3 companions around the 3 system of the 5 targets, and then also we confirm that the 3 detected companion makes the radiosity trends. Also, for the 2 targets with the stellar companion, we limit the object which makes the radiosity trend is here. We constrain the mass and the semi-major axis. We constrain the mass and the semi-major axis. So we revealed that the source of radiosity trends, and also we will do that. The frequency of the distant planets around the intermediate mass giants. That's all. Thank you.
Hi, I'm Anthony Harness. I'm a grad student at University of Colorado. This is some work I've been doing with Northrop Grumman, and we're doing high contrast astronomy with star shades. If you're unfamiliar with star shades, they're an external occulter and a way to do direct imaging. We think they have the best potential to do characterization of Earth-like planets in the near future. But until we get there, we're doing technology development and demonstrations of these on smaller scale star shades. So these are half-meter class star shades opposed to a 50-meter class star shade. The trick to testing these is you need a large separation between the star shade and your telescope. It's difficult to do on the ground. So to do that, we utilize the McMath solar telescope at Kitt Peak, and we use the heliostat to steer a beam of starlight in front of our star shade. So as the star moves across the sky, we can track it and provide a stable beam of light. So the star comes in, hits the main heliostat, diffracts around the star shade, gets sent up and down this tube. We then shoot it out of McMath across the other side of Kitt Peak to 2.5 kilometers away, where we're waiting with our own telescope. And we have another telescope in here that has a closed loop feedback system, so we can control McMath from this far ridge. Next slide, please. And so we are getting about 10 to minus 5 raw contrast on this, down at flight-like Fresnel numbers and an inner working angle of 10 arc seconds. But as you can see, as the atmosphere distorts the path along the way, we start to leak out from the side of the star shade. We are getting misaligned. And so that's kind of a limitation of what we can do with this setup. However, if you guys have any good ideas of how to subtract this is not a very nice stable PSF that the bigger telescopes get. So come talk to me afterwards. Thank you.
Hi, good afternoon. My name is John Bovair, and I'm working with Jason Steffen at the University of Nevada, Las Vegas. As the exoplanets are continually discovered in the Milky Way, They're very important. They give us insight into how planetary systems form and evolve. As such, the system architectures and planetary abundance measurements are extremely important. Now, the Doppler signal that's coming from a single planet with a Keplerian orbit looks exactly the same as a double planet model that's in a near circular orbit with a 2-to-1 period ratio. And interestingly, Kepler has seen a population of adjacent planet models with a 2-to-1 period ratio. In fact, the peak is more around the 2.17 to 1 period ratio. And so to investigate this further, we use the Exoplanet Data Explorer to extract reported single planet systems with masses less than 1 Jupiter mass, eccentricities greater than 0.045, and signal to noise greater than 2. And we use the Systemic 2 console to fit 3 models to each of these systems, a single Keplerian model and 2 double planet models with circular orbits, one with the 2-to-1 period ratio and the other with the 2.17 to 1 period ratio. Now, since all of these models contain the same number of model parameters, we use the centuries-old chi-squared method to determine the preferred model. Next slide, please. And so just some quick results. The 2-to-1 doubles are preferred over the singles in 58.33% of the sample, and the 2.17 to 1 doubles are preferred to the singles in 62.5%. Now, we are currently working at implementing Bid Nelson's FML that we just learned before lunch, and since the chi-squared isn't really the best way at going about this. But if these results prove to be robust, then it may suggest that planetary migration in the disk is more important in planetary formation than previously thought. Thank you. Please see me at poster 5.
Hello everyone, my name is Jennifer Carter. I work with Professor Knuth at the University at Albany. We use nested sampling and Bayesian data analysis to characterize exoplanets within the Kepler dataset. I'm currently looking at the different ways to model reflected light, and I'm going to look at just a couple of them today. One of the standard approaches is to assume that the incident stellar radiation is coming in the form of plane parallel waves. And this leads to, which one of these? This leads to 50% illumination. Another method is instead to consider the star as a point source of light, and you look at the tangents between the planetary surface and the point source. And this leads to less than or equal to 50% illumination. Next slide, please. Instead of doing either of those, it's much better to consider the finite size of the star, in which case you have 2 tangent lines to think about, well, 2 pairs of tangent lines. The inner tangents define the fully illuminated zone, shown here, and the outer tangent lines show the night side, each of which always compose less than 50% of the planetary surface. In between the two, we have the penumbral zone, which experiences partial illumination. And if you consider the penumbral zone and the fully illuminated zone together, you always end up with greater than or equal to 50% illumination. This is important because if you don't know how much illumination you have, you can't really estimate the reflected light very well. This also can lead to better estimation of things such as the temperature of the planet. And I welcome you to ask me any questions or come see my poster at poster number 8. Thank you.